它自己有时候会过一段时间，它自己会跳一下。我继续。
Okay. So now, if you consider the subgraph, let it be G be a subgraph of G by removing two vertices, right? U and W. So you remove this U and W from the graph, and now these two things are gone, right? And for every S is a subset of but H is still going to be a bipartite graph, right? But now U is gone, W is gone. So for any subset is contained in U minus by removing this vertex, right? For everyone here, let me consider its neighborhood of S, which is in H now. Cardinality. Cardinality is because originally I know the cardinality of S in G if I'm not removing U and W, right? So here I claim this is larger than or equal to this -1, because the worst case is W is in the worst case is W is in the neighborhood, right? By removing W, you have one number decreased. But I already made my assumption. I say this cardinal is strictly larger than, right? So this is larger than or equal to the cardinal of S plus 1. Because larger than, strictly larger than, that means that's equivalent to say this is larger than or equal to S plus 1, right? So the first one is larger than or equal to this plus 1. Minus 1 here, that's exactly equal to the cardinal of S. Okay? So therefore, if you look at your subgraph, right, so the cardinality of any set is going to be larger than or equal to the cardinality of S by induction. By induction, right? So which means there exists a matching M, which is in H. But now that's easy. What you need to do is say, let me call this M prime. You let M to be M prime union with add one more match, right? UW. And this is going to be my new match. That's a match in G. Satisfy the condition, right? Everyone in U is matched with someone in W, right? Because by induction, my H has a property, right? So if you look at the cardinality of H is K minus 1, because you remove U from the set. So now the H U minus U, if you remove U from this large set U, and now if you look at H, right? So the cardinality here is K minus 1. So now by induction, there exists such a good matching, right? And then you add one more edge, you get another matching in G, right? So you are done. So in that case we handle it. So now let's consider the second case. So case number 2. Assume this is the opposite. Right? Case 1 and case 2 is the opposite. So opposite of this statement is there exists some S in W such that P implies Q, right? So the opposite is going to be P and not Q. So S is cardinality is strictly less than U, larger than or equal to 1, and the cardinality of S larger than, that becomes less than or equal to the cardinality. But I have a host condition. So this is always larger than or equal to, right? Larger than or equal to and less than or equal to, therefore this is equal. So means there exists a subset such that the cardinality of neighborhood is exactly equal to the cardinality of original S. And now the proof is quite is also very similar to that one, right? So let H be a subgraph of G by removing S and the neighborhood of S. Okay, so now S is gone, and here's G, and this is S. This is neighborhood of S. So now these two things are gone. Right? So now what's left is all of the rest. But at least I know from S goes to neighborhood of S. So from here there's a matching. So let me assume there's a match 1 from S goes to neighborhood of S. Because the cardinality of S is strictly less than cardinality of U, right? So cardinality of U is equal to K. So which means the cardinality of S is less than or equal to K minus 1. So now using the induction, I know the result is going to be true for K minus 1, right? For K minus 1. So there's what we call the perfect matching. So everyone is paired. So that's there's S. Now, if you look at your H, so that's something, S is gone. And this is neighborhood of S, right? Neighborhood of S. So this is S, this is neighborhood of S. And if you look at this subgraph, let's verify Hall's condition is still going to be true. And in this case, let me call this is going to be my U1, this is going to be my W1. First, I know this cardinality of U1 is equal to the cardinality of U minus cardinality of S. But because I know the cardinality of S is larger than or equal to 1, right? So this is strictly less than cardinality of U, so which is strictly less than, right? So therefore, it's less than or equal to minus 1. So that's going to be K minus 1. So first I know the number of the vertices in this U1 is less than or equal to K minus 1. Satisfy the induction hypothesis, right? But I have to verify in this case, Hall's condition is going to be true for this H is going to be true, right? So in other words, is I want to verify neighborhood. So for every I want to say for every x which is in the U1 minus S1, I want to say the neighborhood of x in H cardinality is larger than or equal to the cardinality of x. Right? So that's what I want to prove. So this is what I want to prove. Right? If I'm able to prove this result, then by using induction, so I know there's another matching M2, right? Perfect matching here, and combine these two match, then I will be able to reach my final conclusion. All I need to do is verify this condition. So whether this is going to be true. So now let me do a little bit of computation here. I'm going to consider X union S, which is in U, right? And by Hall's condition, the neighborhood of X union S cardinality is larger than or equal to the cardinality of X union S. But I know X and S, they are disjoint. So therefore, this is equal to the coordinate of X plus the coordinate of S. Okay, so but what is this number? This number is the neighborhood which is coming from the neighborhood of the elements coming from X and S, right? So therefore, it contains the neighborhood of S and something else, right? And something the neighborhood of X, but all of the one inside this set has already been counted, right? So I should count all of the ones which is not inside this neighborhood of S. But not inside this neighborhood of S is exactly in this graph of H. So therefore, if you look at the neighborhood of X union S, right? So neighborhood of S is contained in neighborhood of S has already been here. So if you look at for nx, the neighborhood either be in S or is outside of S, right? For all of the ones of inside of S has already been counted. So all you need to count is the one outside of S. But outside of S is contained in the neighborhood of X under the subgraph of H, right? So therefore, this cardinality plus that cardinality is exactly equal to this cardinality. And now, I know by my assumption, I already know S is a perfect matched with n of S. So these two terms can be cancelled out. The conclusion is neighborhood of X in H, cardinality is less than equal to neighborhood of X. That's exactly what I want. For this subgraph H, the cardinality is less than equal to k minus 1, and also satisfy the Hall's condition, right? And by induction, again by induction, I know there's a perfect match. There's a perfect match in this H, right? So union M1 and M2, you are able to obtain M such that the cardinality of M is exactly equal to S plus U minus S. That's exactly equal to the cardinality of U, so which is equal to K. Right? So you are done. So that's how we are able to prove this result. Right? So for biparty graph, we do have a good way to tell when alpha prime of S and alpha prime of G is equal to the smaller cardinality of the parties, right? And this is what we call the Hall's condition. And a quick corollary of the Hall's condition is what we call the marriage theory. So now if you assume there's in a collection of R women and R men, and I want to find a perfect matching, a total number. So of course if I want to do a marriage, right? Every woman pair with one man. So if I can have a total number of R marriage between a quantity couples is possible. I want a marriage between man and woman. They already know each other quite well, right? So that's a condition for the marriage. A man and woman, they have to be know each other quite well. And when this is possible, there exists R marriage if and only if for every k between 1 and r, every subset of k woman is collectively a quantity. With at least k of men. So in other words, is because if you use a language graph, if a man knows a woman, then you have an edge joins between them, right? So basically means for any subset of S from the woman's, and the number of the men totally know the men what they know, right? Total number should be at least k, right? Should be larger than or equal to the original this number, right? So that's what we call the marriage theory. Let me just quickly stop here. So today basically I just review some result, and next time I'm going to talk a little bit more on the application of this result, right? And how to use this result and discuss a few applications. So today basically I introduce their theories, and then next time I'm going to discuss a little bit of applications. Okay, so that's all for today. Yeah.